Hello again from Digicool Things. It's been a little while since my last video, but that's because I've been busy with this project, having fun with developing it, coding for it and using it. I finally feel that all of my hard work is now ready to share. Hopefully this project will be either of nostalgic interest or educational interest to others, who will get as much enjoyment as I have. So, following on from my last couple of videos, where I first introduced my OLED 128x64 display card, then in my last video I introduced my updated 4x5 matrix hexadecimal keypad. I'm now at what probably could be considered a part 3 of a video series. I now make use of the two prior projects for my latest retro system recreation. There was a sneak preview at the end of the OLED display card video, where I'd already started to experiment with some existing code. As you may have guessed, my updated hexadecimal 4x5 matrix keypad project was inspired by my desire to recreate and rethink the Dream 6800. The Dream 6800 was created by Michael Bauer and published as a project in the Electronics Australia magazine in 1979. The Dream 6800 was my first hands-on microprocessor experience, and it was also one of the first video graphics capable microprocessor systems, way back in the late 1970s. For the Americans watching this video, the Dream 6800 was inspired by the RCA Cosmac VIP system. Both implemented the Chip 8 higher level byte language. Chip 8 was ideal for writing the early chunky video graphics based video games. One advantage I personally believe the Dream 6800 had was that it was based on the Motorola MC6800 microprocessor, which was a more traditional 8-bit microprocessor design of the time, as compared to the more unique RCA 1802 that was used by the RCA system. For this video, I'm actually going to approach things a little differently than my usual video format. I'll first go over the design, but then I'll focus more on the code and the experience of using the finished system, rather than my usual focus on actually building it. I will, of course, still cover the assembly, but in a quicker format, so that we can move right on to the retro 70s experience that the system provides. The recreation of the Dream 6800 not only provides a nostalgic experience for those that grew up during the late 70s, but it also provides a highly realistic experience for those who just want to experience the early days of microprocessor-based computing. In the lead up to my desire to recreate the Dream 6800 on an MECB-based system, I reached out to the original Dream 6800 creator, Michael Bauer. Initially, the contact was primarily to inquire about his website published comment regarding an alternative circuit to replace the now hard-to-find NE566 function generator, or voltage-controlled oscillator, as used in the original design. This led to further email discussions, which also covered some retrospective on earlier design decisions. This was very inspirational. One of the first inspirations was Mike's comment about potentially using a 4x5 matrix keypad to provide an additional row of 4 function keys. This would be instead of the original design's hardware debounced single function key. The ChipOS operating system, which the Dream 6800 implements, uses a single function key in combination with the 0 to 3 hex keys to implement 4 different functions, function 0 through function 3. So it did seem a logical enhancement to instead provide 4 dedicated function keys, implemented as an additional row of the scanned keyboard matrix with software debounce. Further discussion was had around the original interface circuit design, as several of the IC components, which were used back in 1979, were now very hard or expensive to source. The result was designing a new interface, using only currently available components, and also dropping some of the components that were no longer needed. It's fair to say that the new design evolved over time as design issues were identified and resolved. The result being that my first release is as a version 2 schematic in PCB. For reference, here is Michael's original schematic for the matrix keypad, tape interface and the sound interface for the original Dream 6800. As you can see, it uses the now very hard to find NE566 function generator, a 741 dual supply op amp, as well as a 7440 dual 4-input NAND gate, and a 74121 monostable multivibrator. The 74121 is still available, but is now relatively expensive. In addition, you can see the choices used for hardware debouncing a standalone single function key. Note also that the original circuit used a dual supply of +5 and -5 volts for the tape interface. So, here is the version 2 schematic for my Dream recreation keypad, tape and sound interface, which I finally arrived at for the interface circuitry used for my Dream 6809 recreation. Firstly, I've designed this to be driven from the PIO connector on my existing MECB Motorola I card, and also to work with my newly added hexadecimal 4x5 matrix keypad. Secondly, you'll also notice I've included an onboard amplifier and speaker, so it makes for a self-contained board that implements all of the required interface components for an MECB-based Dream recreation. Also, you'll notice it's now powered from a single 5-volt supply, as we have on our MECB system. Apart from this, you can see that a commonly available NE555 timer, combined with a bilateral switch, both in debate packages, replaces the frequency shift keying function of the original NE566. In addition, I've replaced the 74121 with the relatively cheap and commonly available 74HCT123. Also, the 7474 has been replaced with a modern matching 74HCT74. Finally, the original dual supply 741 op amp has been replaced with a common LM358 single 5-volt op amp. This part of the circuit is borrowed from Mike's earlier published single 5-volt changes to the original design. Some other changes are made were to utilise the spare 74HCT74 flip-flop for digital control of the sound output. This replaces the prior use of a 7440 NAND gate and also has the benefit of implementing a divide by 2 on the resulting sound frequency. I personally found the bleeps to be a bit ear-piercing, so dividing the default sound frequency, 2.4 kHz, by 2 made for a more pleasant bleep sound. Okay, so let's move on to the PCB layout. Here you can see the 3D render of my resulting PCB layout. Firstly, note that the PCB is designed to fit underneath the hexadecimal 4x5 matrix keypad, making a nice, tidy and compact interface solution, with all of the circuitry and speaker sound output all hidden beneath the keypad. You simply connect the resultant module to the MECB Motorola I card's PIO port in the same way as my earlier implemented Creative Vision Recreations controller board. Then you just have the two RCA connectors at the side to connect to a tape deck for a realistic retro experience, or for connecting to a PC sound interface. For the speaker mounting, I've also created a 3D printed speaker shroud, which nicely holds the speaker to the circuit board. So next, let's get one of the new interface cards assembled. On my workbench, you can now see all of the components necessary for assembly. As promised earlier, I'll present the assembly in a quicker format, just covering the order I used for assembly. Right, with the soldering completed, it's time to insert some ICs. So let's start with the 74HCT123. Then I've got the 7.4 HCT 7.4. Then we've got the 4 debate packages, starting with a NE555. Then we've got the LM386 amplifier. Then we have the LM358 op amp. And lastly, the bilateral switch. And the circuit board is now fully assembled. So I might put in the 4 corner PCB standoffs, just so it sits nicely on the desk. And I just noticed I've got a couple of leads I haven't snipped off from the speaker. That's better. Right. Now, for some initial tests, I might hook up some power, so 5 volts, which goes to the side pins of the PIA connector. And I'll hook up pin 1 of the op amp, which is the buffered output of the capacitor charge and discharge for the frequency shift keying. So that should give us a nice triangle wave. And I'll also hook up pin 3 of the 555, which is the square wave output. Now I just need some scope probes. Here's my first channel. And the second channel. Just using the ground test point for the earth connection. Just turn on the scope, double check all the connections, and let's apply power for the first time. Okay, we have a nice 2.38 kilohertz, just on 2.4 kilohertz signal. You can see on the yellow channel 1 we have the triangle waveform as the capacitor charges and discharges, and the pin 3 output is showing a nice clean square wave, and you'll notice it's pretty much 50% duty cycle, and there enough. So now I'll just jumper the PB0 line to ground, and you can see we're at 1.2 kilohertz. Perfect. So I can now take that out, and I'll also get rid of the second channel, and I can now connect the scope to the 2 test points. Now I can do a little timing adjustment. Now if you haven't got a scope, don't worry, because I think you can just leave the trim pot at mid position and it'll be about right. But let's take a look. So what I'll do is I'll connect the tape out to the tape in. So I'm creating a loop back. And now I can see what I've got on the scope. So at the default mid position, it looks like we're just under 300 microseconds pulse width. So I might just tweak that a little bit. Right, and now we are just over 300 nanoseconds. Probably about 310 or 320 thereabouts, which should be fine. Just to explain, what we're looking for is a delay which is approximately 3/4 of the wavelength of a 2400 Hz signal. At this point in time, the 2400 Hz signal should be low, whereas the 1200 Hz signal, being half the frequency, will still be high. And that state is then clocked into our flip-flop. So you do have a bit of leeway in terms of the 312 microsecond optimal setting. Right, so with that done, let's disconnect our scope and our loopback cable, and we can disconnect the power. And we should be all proven and ready to go. So the next thing I'll do, I've got some custom keycaps that I designed for the function keys, which are purpose-built for the Dream recreation. So instead of function 0 we have memory modify, memod. Instead of function 1 we have load. Instead of function 2 we have dump. And for function 3 we have go, which I've also color coded. So if I grab a keycap remover, let's get the function key keycaps changed over. So go is function 3, dump is function 2, load is function 1, and memod is function 0. Right, now we can attach our keypad to our controller board. So that just drops on, and I'll turn it over because I want to screw in the PCB spacer screws. And there we have it, one completed Dream interface. All that's left is to plug it in. Now before I do that, let's take a look at the MECB cards I'm using. So in the first slot I have my 128x64 OLED card. In the back slot I have my Motorola I card, of which we're using the PIA, and we're also using the 6840 PTM, which is used for timer 1, which I program for the 20 millisecond tick clock, which is a 50 Hz tick clock, which on the original Dream 6800 was provided by the vertical refresh signal from the PAL video. And lastly, we have the CPU card. Now you could either use just the basic 6809 CPU card, but I've chosen for the moment to use my PLCC version 6809 card, or 6309, with the added ROM expansion. The main reason was so that I have both the Dream 6800 code and the Assist09 code in separate banks. So while it's on, I can just hold the reset in and switch across to between Assist09 and the Dream 6800, which enables me to use Assist09 to transfer files during development. I know that's cheating, but it's a good way to develop things like Dream Invaders, where you've got like 2K of code that you really don't want to key in, which we didn't even do in the old days, because Dream Invaders was a game that we bought on tape. And of course, lastly, we have a backplane. So basically what you see now is all the components needed to build a Dream 6809 recreation. On one more point, the 6809 is being run at 2 MHz. Okay, let's reassemble the cards. And I've got my IDC cable. So the IDC cable can plug into the Motorola I card's PIA port, and I can position the keypad next to the MECB system and just plug it in to its IDC connector, and we're ready to go. I'll just move this across and I'll get a camera sorted out so you can see the display, which of course is right in front of me. Now, while editing the video, I've just realised I'm almost 30 minutes into the video. So I made a last minute decision that this will now be part 1, and I'll return in part 2 so I can properly show you chip 8 and the use of the system. But I'll leave you with a picture of the system up and running, just as a teaser for part 2. That's it. Thanks for watching.